Welcome back. Welcome back. We have another fun problem that's piggybacking off a previous one with momentum and energy, and using a relativistic technique. Again, I think this one might be a little easier, but it turns into an algebra heavy substitution fest here after the fact. But let's dive in. The statement reads, a particle of mass m collides elastically with an identical particle at rest. Classically, the outgoing trajectories make an angle of 90 degrees. Calculate the angle relativistically in terms of phi, the scattering angle, and v, the speed, in the center of momentum frame. So here we get more work with the center of momentum frame. And how do we use this? Well, let's first draw it out. So in center of mass, we say that so let me rewind. In the lab, we have a particle smacking another particle, and then the outgoing is a 90-degree angle here because we have to conserve momentum. We know we're going to the right, so we have zero momentum to the left, everything going to the right before. After, you have to have everything going to the right, and zero going in the vertical. So what this means is that the outbound R and the outbound S in the vertical direction has to be the equal magnitude but opposite in direction. Okay. However, in a center of momentum frame, we need to have momentum be zero in both. So what this tells us is that we need to transform, right, the framing, the inertial frame that we're in, and send one frame going the other way. Therefore, this momentum dies out by half, but this one gains that other half, but in the opposite direction, as to cancel the momentum into a zero before and after. Similarly here, since we have zero going this way, we need to make sure that we have zero going the other way. So although the angle here still might look something like half of this, without the calculations, we still need to push the other one to the opposite side so that we have the horizontals canceling and the verticals canceling, because in the center of momentum frame, we need to have zero in both. So what this means is that we have to have a before and after in both, and we have to be able to transform from before and after and do substitutions with the before and after in the transformations. That's where these problems become a bit tricky, and we just have to be very careful on bookkeeping and the notation. But I think we're ready to attack this problem. But here is the diagrammatic situation and why we want to use a center of mass framing or center of momentum framing versus in lab framing. So let's see what we got. All right, so the solution starts off with, first let's talk or define the center of mass frame. Again, we talked about how that has to be zero. So in the center of mass frame, we see that R mu and S mu are having equal magnitude in momentum, or rather equal magnitude P in magnitude of the three momenta, but opposite in direction phi, the scattering angle from the horizontal. We saw all of that in the diagram. So what we say is that the outgoing four momenta in this frame for the R and the S, so upper and lower, is this, where we have the zero term, X, Y, and Z term. Again, no momenta in the Z direction in this setup here. We just have X is positive, Y positive, and then for the S, both turn negative because this one's pointing left, this one's pointing down. But the E should stay conserved in both. So it helps to work with the four momenta. But this is what we observe, and now we can kind of use algebra and conservation to settle what this angle phi is. All right. In the classical lab frame, we have momentum conservation that gives us a net momentum to the right. So what we need to do is transform the X and Y components of the four momenta from the CM frame to the lab frame. This is where we get the transformations. The Lorentz transformation tells us that we have bar from CM to the lab frame has a factor gamma, has Rx minus beta R naught, again, the 0th component. So cool there. Y stay unchanged. Because again, we have to shove the framework to the right if we're going from CM frame to lab frame. So it's only the X direction that is moving. And then we have SX give us again a transformed coordinate, and SY stay the same. But we need to define beta in terms of E and P, the energy and momenta. We know that the rest mass or relativistic energy is gamma mc squared and P is equal to gamma mv. So where V is to the left, again, we have to shove everything moving to the left in the CM frame in order to cancel a 0 out from the classical limitations. So if we solve things for C and we solve things for V, we get V from here divided by negative gamma, or divide by negative gamma m for momentum. To keep a factor here, divide by gamma mc on E. So that's what we do here. We see that we're divided by a fraction, multiplied by a reciprocal. The negatives cancel, the negative stays. The gamma m's cancel on both, and we get a negative PC over E. So that's our beta factor for this context. We're good there. Now, what we need to do is write out the full transformed coordinates. So now that we see the full set, we have r bar x is equal to gamma, p cosine phi, and then we have the beta term here, and then times what the 0th component was. The reason why, again, we cancel E, cancel C on both of them. And we're just left with r bar equal p sine phi. Again, that should make sense based on the what we saw in the CM frame. S bar, again, E and C cancel. We're good there. The gamma or the beta term allows that. Then we see the negative sign there. So everything's looking pretty good now. What we see as far as a vector for mu not equal to 0, so 1, 2, and 3, is we get the position vector. We see that we have a gamma p in both of these, so we're left with a cosine phi plus 1. After we factor out this p, the two negatives cancel. Now we're left with p sine phi, and then z component is 0. Similarly for s, we have a negative in both, factor that out. With the p, so then we're left with cosine phi minus, and then a minus p sine phi from here. Again, z component is 0. Now that we have that, we're good, okay? What we know about the bar system here is that if we want to find the angle in the lab frame, we simply take the dot product. And that's why we have r bar dot s bar gives us the magnitude r, magnitude s equal cosine, or times cosine. Solve it for cosine. We've seen this a million times. But in this particular context, now this is where it gets gross, and we're going to have to pay attention to the algebra, the substitutions, and the cancellations. That being said, our r bar dot s, we see that we can multiply the x components together, or the mu equal 1 components, and these are the mu equal 2 components, or y components. Magnitude, of course, take each component, square it, add it together, so we lose any negative signs that we may have had. And let's see what we can do. Note that both of the terms and the magnitudes have a p squared in them, and so color coded red and blue respectively, and we'll see them factored out next. All right, since both of the terms had a p squared, and we can factor them out, the square root of a square gives us the p, just the thing back. So we have a red and a blue that we just factored out and let the square root take a power off. So that's how we end up with them outside of the square root. Here we tidied up the numerator a bit after distribution and cleanup, and we see that both numerator terms have a p squared term. So whenever we factor that out, after we distribute this cosine, and so on and so forth, we see that the cross terms of the cosine plus 1, cosine minus 1 leave us just, or the cross terms will cancel, leaving us with just the end terms. So cosine squared and negative 1, or in this case, the difference of squares, which leaves us with a nice substitution later. But nonetheless, we factored in a p squared out of both of them, put both of the p's that we factored in the denominator together, and they cancel with that p squared in the numerator. Voila, we like to see that. Now, this difference of square, we know from Pythagorean identity, can be substituted in, and that's where we get a negative sine squared phi in the numerator. Let's also pay attention to how we have a square cosine term here, or square bracket here, square bracket there. The sign in purple, sign in green. What we can do here is force factor by putting the sine squared in the bracket here, but taking one outside of the radical. Same thing on the purple side. I tried color coordinating this as much as I could, just to make sure that everything was top notch and easy to deal with. But again, this forcing that we have is simply for the identities to be plugged in, and it is quite a mess, but the color coding should help. Anytime you have a square and you could factor it inside the square root, that square factor can be pushed outside the square root. Then as you see here, we have a square sine phi, a square sine phi here. So we factor it out with the negative, and we see the negative cancel, the sine squared cancel with these sine squared, and now we're left with the trig sub in the bracket terms. Again, trying to color coordinate it. Those are the half angle identities for cotangent and tangent respectively. So we plug them in, and now we get this one big square root term with brackets that we can distribute later. We're not quite done yet. We need to tidy this up. We just see here that we can do a little more work. Thank you. All right, so let's go ahead and make the substitution, get everything in that numerator to omega. And the reason we want to do that for the gamma squared minus 1 term was so we could plug this into the gamma squared term down here. So we had to add 1, of course. And when we do this, we get ourselves into another distribution of the cotangent. So we distribute the cotangent here, the cotangent to this one, and that leaves us with a cotangent plus 1, which we see that when we do that, this term and this term are a trig identity as well. So we can, that's a part of the Pythagorean theorem identity, so that's cosecant squared. Similarly, tangent and 1 give us secant squared. So as you can tell, we might wish to do another force factor here. What is secant squared but 1 over sine squared? Or cosecant is 1 over sine, secant is 1 over cosine. So force factor those out, because you have a tangent, which is sine over cosine. This is 1 over cosine. You have a cotangent, which is cosine over sine, and this is 1 over sine. Force or factor them out to where we see here, and this is what I mean by when you factor everything common factor wise in a square root, you can bring them outside. So you get a 1 over sine and a 1 over cosine, but since we're dividing by a fraction, we multiply by the reciprocal, and that's why we see a 1 factor here and a 1 factor here from those two. Nevertheless, that was pretty clever in my opinion to see that through. But what we can do one better is we can get rid of this half angle, we'll go back to a solid angle by revisiting the terms here, and we can put in terms of 1 plus cosine phi and 1 minus cosine phi. And all we're doing is a substitution, so to speak, and what we're trying to do is set us up to where we can cancel out some more. Again, a bunch of algebra tricks, but what this will lead to is our ability to write things in terms of the required partitions of what we need for writing out the momentum in terms of the parameters wanted. At this point, I'm just rambling. You see the work here. Pause it if you need to, but I'm going to go out. We force factor that to get the cosine terms alone, and let's see what happens next. All right, we also reduced the top term by a trig multiplication of the half angles, so we're good there. That we just get a sine phi over there. Now we see that we force factored out the omega over 2 on both of them, hence the 2 over omega. And so you see the square here, we bump it out because it's a square inside the square root. So cancel. we're left there. What's cool here is that we can distribute this. Again, we have the difference of squares. So we have a parenthesis term here squared minus cosine squared. Okay. And what we're going to do now is distribute the square term here into these terms. And again, we're going to allow our color coordination to take a hold of that and show that we have a 1 minus cosine squared, brings us to a sine squared. And we're going to let this green term here be tau squared, so we still have a sum of squares. And it's going to be a really, really cool technique to how this works out soon, so bear with me. So here we have is equal to sine over sine after we plunge that out of the square root, cancel, cancel. And after all of that, we're now in a situation where we see that, so we have this equation for cosine theta, and we can write, and we can create a triangle from it for a more convenient representation. Again, going back to the fact that cosine theta is equal to adjacent over hypotenuse, our adjacent side up here is 1, and our hypotenuse is 1 plus this parenthesis term here. Or, so the hypotenuse is equal to the square root term here, which is this is adjacent and this is opposite. So this is why we had to do so much form matching, so we get the adjacent sides to be equal. This has to be 1, this has to be 1. So here we see that the adjacent is 1 and the opposite is tau over sine phi. Now let's create that triangle and see what's up. If that's the case, and we see that with this triangle, we know that tangent theta is equal to opposite over adjacent, so that has to be equal to tangent over sine phi. Now all we need to do is examine what tau is, which we saw earlier. Tau squared is equal to 4 over omega plus 4 squared over omega squared. So we could factor that 4 over omega squared out, and we see that we're left with omega plus 1. If we write these in terms of the gammas that we originally did the substitution on, which will give us back to the angle or the speed and whatnot, we can do a lot of easy work with that. Again, this kind of force factoring technique after we cancel out in the denominator, pull it out, cancel, cancel, and then simplify down. A lot of this is just a matter of algebraic techniques just to get everything wound down. So what we see after the fact is that we get a square term here, take the square root. We see that tau is actually equivalent to 2c squared over gamma v squared. So we have the velocity that we were interested in. And now tangent, which if you remember way back in the chapter, we saw how tangent transformed. Now we have the transformation of tangent in a different context as a function of phi and v. So now that we have tau over sine, we can relinquish and reduce that to 2c squared gamma v squared sine phi, or we can use theta equal tan inverse, of course, to find theta. But we were able to find theta in terms of phi, which was in another reference frame, and v, the speed of the transformation frame itself. So this was much different. And again, all that algebraic work was simply to create a setup to where we could read off what the triangular component of a cosine function was in order to examine the angle, which we could have done just by cosine, taking the arc cosine early. But since we already had to develop something for tangent earlier in the chapter, now we get to compare it. And boy, was that an adventure. I don't think it was too hard, but I definitely think the algebraic jungle gym that we had was fascinating to work through. And for me, I just kept asking myself, why? And then after you see the result, you're just like, that was clever. But nonetheless, quite annoying to deal with in the interim. But cool result, and we see how the transformation angle isn't always what we think it is. Until the next time.